Hello, everyone. So we're back with another wonderful example for lecture 7. So I'm going to go ahead and get my screen to share, and we can go ahead and get started on our OneNote board and work through example 3 in the lecture. So for this example, we're looking at determining the relative reaction rates for a simple first order reaction. Which I can say, when A goes to B, reaction of A is K times Ca, which if I plug in the Arrhenius equation, I get K naught, the exponential, negative E over RT times Ca. Now, we're going to assume Ca is independent of temperature. And then we'll bring this temperature dependence back at the end to do our final calculation. So the first case we're going to look at is when our activation energy is 20 kilojoules per mole, or 20,000 joules per mole. So if I use base case ratios, I can say my relative reaction rate is equal to K naught, the exponential, negative E over RT2 times CA2 over K naught times the exponential, negative E over RT1 times CA1. Like I said, for now, I'm going to just ignore the concentrations. We'll look at that here in a second. And the pre-exponential factor isn't going to be influenced by our temperature change, which we're looking at T2 is 350 degrees Celsius and T1 is 320 degrees Celsius. So this gives a relative reaction rate that looks like this, negative E over RT2 over the exponential, negative E over RT1. So if I use the law of exponentials, I can rewrite this base case ratio by bringing up the denominator and simply write it like this, 1 over T2 minus 1 over T1. And so now what I can do is plug in the numbers that I have and solve directly, or the exponential of negative 20,000 joules per mole over 8.314 joules per mole Kelvin times the difference of the temperatures, which is 350 plus 273 minus 320 plus 273. Now, if I plug that in and solve, I get an answer of approximately 1.22. So for case B, where my activation energy is 80,000 joules per mole, I use the same expression. Negative Ra2 over negative Ra1 equals the exponential of negative 80,000 joules per mole over 8.314 joules per mole Kelvin, and using those same temperatures. This gives me an answer of about 2.18. So that's the influence of the Arrhenius expression on temperature. But what about concentration? Well, I know I can write concentration in terms of partial pressures, which lets me know that the concentration is inversely proportional to temperature. So looking at Ca2 over Ca1, that base case ratio becomes T1 over T2. So solving for that concentration dependence, I get 320 plus 273 Kelvin over 350 plus 273 Kelvin, or a factor of about 0.95. So then finally solving for A, my relative rates equals 1.22 times 0.95, which is about, if I can remember correctly, 1.16. And for B, my solution then becomes the 2.18 times 0.95, which is equal to 2.09. So from here, you can see just how much the influence of activation energy is on those relative reaction rates, right? So we have the high activation energy has a much greater influence via the temperature. All right, guys. Nope, that's all I have for this example. Thanks for listening. Take care and have a great day.